we spoke about extinction, and we're going to talk a little bit about ignition today. There is a bit of description of different ignition sources, and the comment here that the strength of the source is usually inversely proportional to time. I'm sorry. And so the strength of the source is inversely proportional to time, so of course strong sources ignite faster. An important thing that I want to mention is that the ignition limits are not the same as flammability limits. Flammability limits relate to condition on composition or pressure beyond which a combustible mixture cannot be made to burn. Which means that a self-propagating flame cannot be sustained. But that's irrespective of the ignition source, right? So ignition is something else. Now there is a bit of description here of, it's mostly phenomenological on the minimum ignition energy. You can read it or can find it in most textbooks. And I will skip that and move to thermal explosion and ignition. And the first comment here made is that thermal explosion and ignition theory are basically the same concept. They both depend on the rate of energy released compared with the rate of energy dissipation. In one case, the objective is to prevent explosion. In other words, you want to have more dissipation so that the mixture does not explode or ignite. In the other case, of course, you would like to enable ignition. But essentially, they are the same concept. The typical questions that one asks in thermal explosion theory is, first of all, what's the criteria or to determine a criteria that predict whether explosion, ignition would occur or not. The second question that may be asked is what we call the delay time, which is the thermal induction period that it takes until ignition or explosion occur. Of course, an important question is what is the time history of the induction time and the explosion that follows. Here we're going to really focus on the first two. Clearly, the latter require a complete numerical integration of the equations. And we're going to start with the simple Semyonov theory and then move to the Frank-Kamenetsky theory. So the Semyonov theory is based on the idea that the mixture is homogeneous. And so suppose that you have a homogeneous mixture in a given volume, a fixed volume. So think of it as in an insulated vessel. And adiabatic means that there is no heat losses. So the vessel, as I just said, is insulated. And then you want to write the conservation equation. Since there are no special variation inside the vessel, it's assumed homogeneous, then the time rate of change of the internal energy should be equal to the heat generated by chemical reaction. And similarly, you have an equation for the consumption of the fuel or the reactant. Now note that the energy equation, because it's a constant volume, then it's the internal energy that we are that describe the entire energy. And so you have here a C sub V, specific heat at constant volume, rather than specific heat at constant pressure that we had used yesterday and before in the governing equation. So the problem now is a simple first order ODEs for the temperature and the mass fraction of the reactant. And the mathematical setup is that given some initial condition, T naught at time 0, Y naught at time 0, then how does the variation in time occur, and when does explosion occur? So in this problem, we'll be able to determine an ignition time or an explosion time, essentially, if it occurs. But here it will always occur because there is always heat generated and there is no dissipation. Okay? So when we move to the next section, which is, will include heat loss, then we would have a balance to worry about. So the first thing is that we can see right away that by adding the two equations after multiplying the second one by the Q, the heat release, all the other symbols are known to you already. They are the same. I've been using the same symbols all along. So if you add them, you get essentially the total energy, if you like. The time rate of change of that is 0, so it's conserved. And essentially, since you can apply, that's a constant, right? The quantity in parentheses here. Since you can apply the initial condition, then immediately you have a relation that relates y to t. In particular, if y equal to 0, the relation gives you the equilibrium temperature or the adiabatic temperature under constant volume. And remember, we derived an expression for that before, and the equilibrium temperature was similar to the adiabatic flame temperature, but here it's the CV that is different instead of CP. And I have already noted that since CV is always smaller than CP, that this temperature is higher than the adiabatic flame temperature, which is obtained under constant pressure conditions. So if we know what this temperature is, then this relation tells you essentially that the concentration of the reactant is proportional to the difference between the equilibrium temperature and the temperature at a given time, T. So with that relation, we can substitute it on the right-hand side, and the resulting problem is a single equation for the temperature T, which is written here. In addition, we have normalized things. We have put this equation in dimensionless form. So T was scaled with the initial temperature T naught. So it starts from 1 and it goes to the equilibrium temperature. And the equilibrium temperature now in dimensionless form is simply 1 plus Q. The little q is essentially the heat release scaled with respect to the initial enthalpy of the mixture, CV T naught. Initial internal energy, rather, of the mixture, CV T naught. And the other parameter is, of course, the activation energy parameter, which appear in the exponential. So the problem is this, and what we have is to integrate from 1, and clearly after a long time when the equilibrium is reached, the equilibrium will be reached when all the reactant is consumed, then T is going to be equal to the equilibrium temperature TE, right? Okay, now this equation, it's a first order equation, can be integrated exactly. It's a separable equation, so if you integrate, you get that the time T is this combination of the exponential integral function. It's a tabulated function, but the solution is not very transparent from this very convoluted form of exact form. And so it's convenient to look at a limit, and the limit is, again, use the fact that the activation energy is typically large. And if the activation energy is large, it indicates that the right-hand side is going to be essentially small, so the temperature starts with the initial temperature until significant change occurs. And so, this is typically a type of solution that you are going to obtain. This is the temperature, start at 1 until it reaches equilibrium. And you see, as beta naught, the activation energy become larger and larger, then the transition is sharper, okay? And that is exactly what actually we are interested here, because we are interested is when does ignition occur? When is there something that drastically happened to the temperature? So essentially, ignition is an asymptotic concept, because from the green curve, you cannot identify something special that will signify ignition. Rather, from the blue curve, you see that there is a very sharp change here that we would like to address. So when beta is large, the temperature remains close to 1 for a significant amount of time until it starts blowing up here. And there is what we call a thermal runaway, as we shall see. So it's convenient in that limit, therefore, to expand the temperature as is done here. So the temperature is 1 plus a perturbation. The perturbation is phi, which is a deviation of the temperature from the initial temperature. And if you substitute this expansion into the governing equation, you obtain an equation for phi, which is very simple. dφ dt is q e to the phi. Q is the heat release parameter that we had before. And since initially at t equal to 0, the temperature is 1, then clearly phi must satisfy that at 0 it's 0. In other words, there is no deviation from the initial temperature. Well, that equation now is very easily integrable, and the solution is phi equal to minus the log of 1 minus qt. So you see that the solutions start increasing, as is shown here, and when t approach 1 over q, then the argument in the logarithmic is 0, meaning that the logarithmic is negative infinity. With this negative sign, it becomes positive infinity. So you see that the deviation of the temperature from the initial temperature increase rapidly and become infinite at some point that is exactly 1 over q. And that is what we refer to ignition. So there is a very clear criterion for ignition in this asymptotic limit, which is not so obvious or clear if you would use, let's say, the entire solution for any finite beta. Of course, you can choose the inflection point to be such a value or anything else, but it's not it's not a clear criterion which is independent of your ad hoc choice. Okay, so this is the determination of the ignition time, and now we can recast this t equal to 1 over q into dimensional form, and in dimensional form we get a very clear dependence on all the physical parameters. In particular, we see that it's inversely proportional to q, or y naught, and to the reaction time, b beta e to the minus beta naught. So the ignition, actually the ignition time is the reciprocal of that. And so the ignition time is found to, of course, increase. It's going to be larger when q is increased. Q is increased. Oh, I'm sorry. The ignition time decreases. It didn't seem right when I say increases. So the ignition time decreases, becomes shorter when the mixture is more energetic, or when there is more reactant, or when the reaction, or if the reaction rate increases, okay? Or the reaction time decreases. Okay, so this is the first step of the Semenoff theory. The next one is consider now that we have a non-adiabatic system. Still, we consider the system to be homogeneous in this volume, and so again, the time rate of change of the energy is the energy produced, right? The energy which is produced by the chemical reaction minus some heat loss. And we introduce here a phenomenological heat loss, which is going to be a loss from the temperature of the gas inside the volume, which is assumed to be uniform, to the temperature outside. So the loss will be proportional to the difference in temperature. And of course, it will be proportional to the surface of the vessel, S. And the volume comes here because these two terms on the other side of the equation are per unit volume. So if you multiply by the volume, you're going to have here the ratio. Okay? So the ratio gives you some length scale of the problem. And now, again, I want to recast this problem in a dimensionless form. And so I use the temperature T naught, which is the initial temperature, to scale the temperature. And from these two terms, I can produce one dimensionless number, which I call D. And essentially, it's a ratio of the conduction time, which is in the numerator here, to the reaction time, which is in the denominator. So it's some kind of Dam-Kohler number, if you like, multiplied by the heat release parameter. In other words, there are two parameters, but really effectively the problem reduced to a single parameter, which is the product of the two. And so this is the equation now we have to solve. Now, this equation is more complicated, and even though it's a first-order equation, we cannot write an exact solution, simply because when you, since it's separable, you can bring the right-hand side to the denominator, but we don't know how to integrate that equation exactly. We can do it numerically, but not exactly. Well, but it pays to do some analysis. So first of all, to understand what the system gives you before you integrate it to obtain the time history. If you want to get the whole time history, you have to integrate this equation starting with the initial condition and evolving in time to see what it produced. So the first thing that you ask is, are any equilibrium solution? Are there any steady solution to this problem? Steady solution means that the temperature does not change in time anymore, right? So if there is a steady solution, it's going to be a balance between the heat produced by chemical reaction and the heat that is dissipated, or the heat that it's lost through the walls. And so it's going to be a solution of this algebraic equation, which is the right-hand side of the equation equal to 0. Well, to solve this algebraic equation, it's complicated because it's also a transcendental equation. But it can be done by graphical method. In other words, what you do, here is the equation. What you do, you graph the left-hand side, you graph the right-hand side, and you find out when they intersect. The intersection indicates that it's the point or the place where they are both satisfied, which is indeed the solution. So the left-hand side, this exponential is here. It's the red curve. And the right-hand side is straight line. So we plot them versus temperature, right? Because we are asking what is the temperature when equilibrium occurs. So, so the right-hand side is a straight line, but the straight line depends on 1 over d, which is this Dam-Kohler number, which is the slope of the line, right? So, for example, the blue curve have one slope, and if you and the green curve has a different slope, right? Well, the blue curve intersects at this point, so T1 will be the equilibrium condition for that value of d. And if you keep on the slope in this direction, the slope decreases, which means d increases, right? So the green line have a smaller slope or a larger d, and now it intersects at this point, at the green point. But of course, if you increase d further, it will not intersect at least, the lower part of this S curve. And so there will be no steady solution or no equilibrium solution. So this point, or the green curve, correspond to the critical condition, and for d, and a steady solution exists only for d less than d critical. So again, I repeat what I said before. If d1, for d1, which is the blue curve, d1 is less than d critical, a steady state exists, and it's T1. And here the energy dissipated is dissipated at a rate which is faster than the heat produced. And so eventually the system will go to an equilibrium state, which is T1 as t going to infinity. For d bigger than the critical value, the energy generated by the chemical reaction is generated at a faster rate than it's dissipated, and so eventually explosion would occur. So what is the time history of this problem? I will show you in a minute, at least a sketch of it. But to determine the critical value of d, or the critical condition, it's very simple. The equation must be satisfied, but also the two slopes at that point, because it's tangent, the straight line is tangent to the S curve, and so the two slopes should be also equal. So here is the equation is here after I multiply d to I brought d to the left-hand side. And if you differentiate this with respect to t, you get this. This gives you 1. And so now we have two equations with two unknowns. One unknown is t, the temperature. The other unknown is the Dam-Kohler number d. And you can solve it exactly and get an expression for the critical temperature and for the critical Dam-Kohler number. In particular, you can also simplify those expressions using the fact that the activation energy is large, but that's not important. It's important only because it gives you some simpler expression, but that's all. So here is the time history for the two cases. You see in the for D1, which was below criticality, the temperature rises and eventually reach the equilibrium state. But for the green curve, which is above criticality, it's not the same green as in the previous slide. The other one was exactly at criticality. Here it's above criticality. Then clearly it will eventually explode, and or there will be, as we call it, thermal runaway at a finite time, and that finite time is identified the explosion time or the ignition time. Again, it's an asymptotic concept that can be identified very clearly, right? Because, yeah, so that's what you get. So now with the, what I wrote here in the box is what come out from the criticality condition, which we have derived here, but I have also further simplified it for large beta naught. You see that for large beta naught, this expression just get a somewhat simpler version, but it's not, again, important. It's not crucial. What is important is that this critical condition give you information that is useful. So for example, if you ask what is the minimum mass that is needed for explosion, and so so you have to solve for rho y. So rho y gives you the mass of the reactant, and at criticality, it's equal to this amount, right? So any mass above that critical value will eventually explode. We didn't say when, it will eventually explode. Eventually meaning after, of course, that time have elapsed from to T explosion. Or you can ask the question, what is the critical pressure? And so it will tell you that the pressure, again, you solve here for the pressure, and what you do is you use the equation of state to replace rho, and you obtain expression for the pressure. It tells you what's the condition above which the system would explode. Similarly, you can ask a question, what is the size, say, of the volume of gas? And it doesn't have to be gas, because actually it's any material will satisfy essentially the same equations. And you obtain that from the ratio S over V, right? Or V over S. It gives you the size of the of your volume that will explode, right? Above which explosion will occur. Okay, so we dealt with, oh, and one can estimate the explosion time for large beta, and you can get actually a nice simple expression like this. By the way, you see in the denominator there is a term here that can become 0, or right, can become 0, which, and also negative. But when it becomes 0, what does it mean? It means that the explosion time is infinite, which means that the steady state will be achieved. So in fact, delta equal to 1 over E is exactly the critical condition. And so you're not gonna, and so this relation is only relevant for condition above criticality when there is an explosion. Okay. So the next one is the Frank-Kamenetsky theory. And now in Frank-Kamenetsky theory, the difference is that we do not assume anymore that the mixture or the material is homogeneous, okay? In other words, there is temperature variation or spatial variation in temperature. And so the energy equation now would be time rate of change of the energy, heat conduction that is happening inside the vessel equal to chemical reaction. And of course, the temperature initially would be you have to add now two things, one boundary condition and also an initial condition. So let's say that the temperature at the walls is T naught, and you can also assume that you start, let's say, from some initial temperature. Doesn't have to be T naught. Since I'm not going to be solving the time evolution, I did not specify the initial condition, but in general, you should specify one. Now, if you rewrite this problem in dimensionless form, again, there is only one parameter that pops in, and this is this little delta, which is actually quite similar to the previous one. By the way, just an important point, you see the previous problem, what we have done is instead of actually putting the Laplacian, which is the Fourier law of heat conduction, we have replaced this with a phenomenological term, which is T minus T naught, right? But this is, of course, the more accurate description because the loss occurred through the walls, and it's because the wall is at a temperature T naught, which is different than the temperature inside the vessel. And temperature inside the vessel need not to be constant. Okay, so the only parameter that appears is this. Again, it's the heat release multiplied by this ratio of conduction time to reaction time. It's like the damn color number that we have seen before. And the equation is written here. And so again, what we want to ask is, are there steady states? In other words, are there conditions, or under what conditions would the heat dissipation will be balanced by the heat generated by chemical reaction? So we set dt by dt equal to 0, and this is the problem that we are left with. Now it's not an algebraic relation, but it's a differential equation. It's a partial differential equation in general, and this problem is known as the Frank-Kamenetsky problem. Actually, to be more precise, the Frank-Kamenetsky problem is known, it's what's in the box. In other words, Frank-Kamenetsky already introduced this idea that the activation energy is large, and so he introduced a perturbation of the form T equal to 1 plus a correction phi, and when you substitute it in this equation, you obtain Laplacian phi from here, but the exponential here gets simplified. Instead of being like something over T, you get e to the phi. Of course, it's somewhat simpler than the Arrhenius exponential, and this is often known as the Frank-Kamenetsky approximation, and this is the Frank-Kamenetsky equation. Now, since phi is the perturbation, phi at the wall should be 0, right? Because T equal to 1 was assumed at the walls. So again, the question is, are there solutions for this problem, and how do they depend on delta? And so, the typical problem that have been solved in the literature are either a slab, which is in Cartesian form, a cylinder, right, which is in cylindrical coordinate, or a sphere, which is in spherical coordinate. Other configurations are complicated, and so you have to define the boundary if you want, and so on, which of course not standard, and so that's not found in general. And if that's what your interest is, then it's possible to do it, but you have to solve it numerically according to the geometry that you have. Now, the first two, the slab and the cylinder, turn out that can be solved almost analytically. Actually, it's interesting that the cylindrical case can be solved exactly. The other one is reduced to an algebraic equation to obtain the critical condition. The spherical problem needs to be solved numerically. There is no exact solution that is known. And so here are, in fact, the solutions and the graph of, now remember that since the temperature vary inside the vessel, so we are asking the maximum, where is the maximum temperature, and how does the maximum temperature vary with the parameter delta, which is that damn color number. Now, if you assume symmetry, clearly in the slab it's going to happen in the middle, in the cylinder at the center, and the sphere at the center. But you don't need necessarily to assume symmetry. These solutions are for symmetric condition. Of course, part of the domain, part of the sphere could be at one temperature, part at a different temperature. For example, suppose that you have a hemisphere of material, and the hemisphere is subject to the outside temperature except the bottom is subject to a different temperature. So clearly you have to solve it to different boundary conditions, right? So it depends on the geometry of the problem. And here, what you see is that the value so what I have represented here is in fact the solution for different value of delta, which means for a given value of delta, then this is the value of the maximum temperature that you would get in the slab, right? Because that's the solution for the slab. In other words, there is a temperature distribution, and the maximum temperature attains this value. And as you increase delta, it will attain clearly a larger value up to this point. And if you try to increase delta above that value, there are no steady states, so explosion occur then. So for delta bigger than this value, you would have explosion. And this value for a slab is 0.88, for a cylinder is 2, and for a sphere it's about 3.32. You can find more discussion in this book by Harris. It's an old book, and I'm sure there is more discussion in the literature about this. Again, you have you have here a dependence on all the parameters, so you can answer the same type of question that I posed before. What is the volume above which explosion would occur? What is the pressure above which explosion will occur, and so on. So depending on the problem that you're setting up, you can determine the critical condition. Okay, so I think that's it. Yeah, and so the next topic that we are going to move to, oops. Oh, come on. Just a minute. Okay. So the next topic that we will discuss is diffusion flames. And this is okay. So yeah.
What if there's like a meat flow and mixing? Would some of these ideas still cover that?
What is it? What?
What if there's mixing and transport?
And then the question is to find well, there are no, simple theories for this, but of course, some of this idea would occur there as well. It's just that the criteria for explosion or ignition will depend on these additional factors. For example, it will depend on the convective transfer, if you have radiation, on the radiation transfer, and so on. So things become more complicated. The ideas in this simple situation is just to identify, let's say, how we should identify explosion or represent it, right? And then, it's typically a numerical problem, and you can use similar criteria to make this determination. Okay, so diffusion flames. Until now, we spoke about combustion of premixed gases. In other words, we had the fuel and oxidizer very well mixed at the molecular level before ignition occurred and before the flame, a flame propagated through this mixture. Now, the fuel and oxidizer come from different origin, and in order for chemical reaction to occur, they need to be mixed, and chemical reaction and mixing would occur essentially simultaneously. if it mixes before and then reacts, so in principle, it's like similar to a premixed condition after the mixing happens. So we are interested more in the extreme, in the other extreme situation where they are initially separated. And the candle flame is, a very good candidate and a complicated one, despite its very simple appearance of a diffusion flame. It's complicated because it's an interesting, actually, fluid dynamical problem. If you look at the candle flame after it got established, you will see that there is a little pool of liquid, a little pool. Usually it's a small cap of liquid wax which melts, and that is drawn by capillary forces along the wick, and then that is evaporated, and if there is, of course, oxygen outside, it will burn, and the highest usually temperature are in the blue region here. Then there is all kind of chemistry effect, carbon particles that are produced and so on that produce this luminous zone, and on top of this there is also natural convection that where the hot gases rises due to buoyancy and provide this elongated flame that you are all familiar with. So it's a complicated problem, and I don't think that there have been many attempts to even describe it fully in the literature, although there have been some. But anyway, I do not intend to discuss or cover this more. There is a bit of description here that you can read later. Essentially, what is important here is that you need oxygen entrainment to reach the surface where the fuel has evaporated and diffused in order for the two to meet, mix and react. And so since the primary mechanism is diffusion, then the flame of this non-premixed system is usually referred to as a diffusion flame. And we are going to see that later again. So here is, in fact, it's an interesting picture of a candle flame that is burning at 0 gravity. It was in the space shuttle taken, this picture by people at NASA. And what is interesting is that you see that even in the absence of natural convection, just by diffusion, the fuel and oxidizer can meet and react. Okay, so it's the mechanism here is simply purely diffusive, right? Diffusion only. Here are the simple configuration that that have been typically studied in the literature. This is a jet diffusion flame. The fuel emanate from this jet and burn with the outside, with the oxidizer which is outside, or the air outside. This is another configuration that we discussed before for premix combustion, but now what you have are two burners that are aligned and the two jets, one of fuel and one of oxidizer, impinging against each other. And so you have, in principle, a simple flow, which is a stagnation point flow, as we referred to, that we discussed in the context of premixed flames. And now you will have a diffusion flame that is established. And it can be established either on the oxidizer side or on the fuel side. And we're going to see later a discussion that tell us how to obtain or under what condition it's on which side. And then another simple configuration is a droplet, and we're going to discuss that in the next lecture. So you have a fuel droplet, a liquid droplet, let's say, that evaporate, and the fuel vapor meet the outside oxidizer and burn. Of course, in reality, due to gravity, the flame will be somewhat elongated on top. It will look more like a teardrop. But at zero gravity, people have observed indeed spherical flames that enclose the droplet. An alternative flame, which is also similar to this, is a spherical burner. So you inject the fuel either as liquid or as gas, if you like, at a fixed rate, so that and that's a porous sphere, and so the fuel will leave, either will evaporate and leave, or will leave essentially in all directions, so you get almost a spherical symmetry condition, and so you will again obtain a spherical flame. So these are the typical examples that you will see in the literature, and those are the simple ones that we can discuss and extract some information. Now, you see, probably one of the simplest that you may think of is this one, because the flame is flat. And so you may ask yourself, why not studying a planar flame? Okay, like we started in a premix combustion, we study a planar flame. So let's suppose that you have a one-dimensional flow. Okay, so the mass flux across the entire say tube is m, or m tilde in dimensional form, and so the fuel is supplied in that stream. Okay, so you have a stream, fuel is supplied in the stream, and let's say that oxidizer somehow come from the top and is establish a diffusion flame. Well, there will be, of course, and so in principle, if you want to maintain a one-dimensional problem, the type of condition that you would impose is that in the stream far away, the temperature is known. There is, I'm sorry, the stream is the top line. So the temperature is known. There is fuel in the stream and no oxidizer, and oxidizer is supplied at some boundary at the top as specified here. Well, unfortunately, this does not work, because there will be product that will diffuse on both sides, and as the product diffuse out, it's going to change the concentration at the boundary here, x equal to 0, and so you cannot maintain constant properties. Why not, as I have indicated? So this is not, in principle, it doesn't seem that it works. In other words, experimentally, you cannot set that up. In fact, the question is, why should I move this boundary to infinity? Well, you will not get a mathematical solution, and the reason for this is very simple. Suppose that you have such a flame, then beyond the flame, namely on the side, side which is x bigger than xf, then essentially your problem is going to be solving a convective diffusive, and I'm writing this for the oxidizer, a convective diffusive problem like this, equal to 0, because reaction occur only in the blue region. Well, if you have, in fact, you would have also a diffusion coefficient like that. So solution of these equations are of the form, they are proportional to a constant plus another constant e to the m tilde over rho d naught x. In other words, they're going to be infinitely large at infinity, so C2 must be set equal to 0. And so the only possible solution are going to be constant mass fraction. But constant mass fraction is in contradiction with the fact that at the flame, all the oxidizer had to be consumed, so it's not going to work. So there is no one-dimensional planar flame, diffusion flame in the unlimited space from negative infinity to plus infinity. If I supply condition at 0, it's possible to find a solution, but then the question, how do you establish this experimentally, or how do you establish it in the lab? And in fact, it was done, but only very recently. And note that I call it the steady planar unstrained flame, because in a counterflow, you also get a planar flame. But clearly, this one is under strain, right? It's always under some stretch, okay? Now, the unstrained flame was observed in a very peculiar, or in a very interesting, or if you like, ingenious experimental apparatus that is shown here by a group at the EPFL with Peter Mankiewicz. That I was part of that, but of course my involvement was more in the theoretical aspect of this. And the idea was to supply the oxidizer on top from very small needles, and there were about 600 to 800 needles that supply the oxidizer. They were set apart they were put at close distance of each other, but in a symmetric way, in such a way that the product can just escape in between, okay? And so, in fact, since you have the oxidizer coming in from the needle, you may ask, well, the flow cannot remain one-dimensional. Well, it's true locally. And so what you have is that this is the blue region where the oxidizer come in, and then because it's pushed by the uniform flow, it's going to turn around and leave together with the product in the distance between the needle. And experimentally, here are measurements of the vertical velocity, and you see that after about 2.5 to 3 millimeter, the velocity is again uniform. So there is a virtual boundary condition, which is here shown that the green line where the flow is basically again uniform, okay? And here is just data that show you that the velocity is almost vertical, and it was controlled here at 60 millimeter per second, and that the horizontal velocity is nearly 0, very small variation. In fact, this is the stretch rate that show you that the flame is nearly unstrained, or 0 stretch. And here is the picture of the flame, which you can see that it's very flat and planar, okay? This is another view of the same flame, and what was in the middle was a cylinder that was inserted just to avoid some boundary condition, but that's for a different reason, so that's not important. So this is what, this is a side view, of course, of the flame. So anyway, the point is that one can indeed establish a planar flame in such a configuration, and the proper boundary condition is, as I've stated here, which is what I stated before, should be applied at some position which is not exactly at the exit of the needle, but just close to the exit, distance of about 1 diameter or so. So M is prescribed, and the problem that we are interested to solve is to find the location of the diffusion flame and the flame structure. And again, we're going to focus on a one-step overall reaction of the form fuel plus oxidizer go to product. Of course, for a diffusion flame, it's the simplest scheme that you can think of. You need both fuel and oxidizer. Okay, so, one more comment. You see, you can think of a similar situation, which is the symmetric one, that I can supply oxidizer with the stream at the bottom, and the fuel will diffuse from the top, okay? Well, mathematically, the two are equivalent. It's just that you have to interpret fuel as oxidizer and oxidizer fuel, because mathematically what I call YF and what I call YO, if I call them oxidizer or fuel, is just a notation and nothing else, right? Okay, so the equivalent problem is solved simultaneously, just you have to interpret it properly. So here is a rewrite of the equation when we wrote them in dimensionless form. So we chose the unit speed as u, which is something that you control, that's the supply stream. The unit length is the thermal diffusivity divided by u, and so on. The rest is straightforward. So you have equations that you are already familiar with. In the diffusion term, you have the two Lewis number of the fuel and oxidizer, and here's a reaction term where D is the Damkohler number, and the Damkohler number is the flow time, right, which is dictated by D thermal divided by U squared, divided by the chemical reaction time, okay? And what is important is that D is, in fact, the Damkohler number is controlled by the velocity of the stream, which is coming from the bottom. So essentially, as the flow rate increases, the Damkohler number decreases, right? That's what you should remember. Okay, so this is a simple setup. So using this, we're going to see how to analyze, first of all, simple diffusion flame, and then we will look at some more complicated examples. The idea is, the first idea is what is often referred to as infinitely fast chemistry, or the Burke-Schumann solution, the Burke-Schumann limit. This is not the Burke-Schumann problem, which I will deal with next, but this is the same idea that was introduced by Burke and Schumann. And the idea is to, well, this is a more modern, if you like, version or view of it, but essentially it's the same. The idea is that if the chemistry occur infinitely fast, which is equivalent to a very large Damkohler number, right? So D going to infinity. If in the equation D goes to infinity, it implies that the product YF, YO in the chemistry term should go to 0. Now, in a premix situation, that is not a good way to, or that's not a good description of the problem, because if those are on the same side of the equation, then there is no reactant, and it's like getting no solution. But in a diffusion flame problem, since they come from opposing end, then it's possible to have a solution that YF vanish on one side of the flame and YO vanish on the other side of the flame, and they still satisfy this relation. And so this is the essence of this limit D going to infinity. So the combustion field is split into two regions, one on the fuel side where there is no oxidizer, which is X less than XF, and one above the, on the oxidizer side when there is no fuel, where YF is identically 0. And now the location XF is one that need to be, of course, determined. It's where the reaction occur, or the location of the reaction sheet. So the I'm going to show you the solution for this simple one-dimensional problem. It's also because the equations are easily integrated in this version. That's why I chose this to start with. But I'll show you two ways of finding a solution. One, when you assume that the Lewis numbers are 1, are all unity, and then I will generalize it for non-unity Lewis number. Now, for unity Lewis number, the idea is that you can use the coupling function that we have discussed earlier. So here is one of them. One of the coupling function is essentially the difference between the fuel and oxidizer mass fraction. Now here are the equations. Since the oxidizer equation has this stoichiometric coefficient, if you divide YO by nu, then the two equations have the same right-hand side. And if you subtract them, you get a reaction-free equation, or a conserved scalar. YF minus nu YO will be a conserved scalar. So here it is. The equation that it satisfies is going to be convection minus diffusion equal to 0. So it's a simple solution to find. It's the same as what I wrote on the blackboard before. And if you satisfy the boundary condition, you obtain what's in the box. You can easily see that as x goes to negative infinity, this is 0, and so YF is the fuel value. There is no oxidizer, right? And when you approach 0, e to the 0 is 1, and then the fuel cancel out. There is no fuel, there is only oxidizer, so it satisfies the appropriate boundary condition, okay? So that's the solution of this coupling function. Now, the nice thing in diffusion flame is that if you set them both equal to 0, YF and YO, that happens when X is XF, So immediately you have an equation for the location of the reaction sheet. So XF is given by 1 over m, the log of whatever the quantity here, which I call 1 over phi. And phi is very similar to what we call in premix combustion equivalence ratio, except that there is no exact there is no meaning to equivalence ratio in a diffusion flame, because the ratio of fuel to oxidizer, the mass of fuel to oxidizer ratio change as they diffuse against each other. But what I have referred to phi here is the ratio of the mass of fuel in one end to the mass of oxidizer in the other end. And I like this notation, or this term better than equivalence ratio, which is somewhat confusing, and I will call it an initial mixture strength. So that's the initial mixture strength. In other words, it's what you provide at the relevant boundaries relative to stoichiometry, okay? If phi equal to 1, it means that the fuel on the fuel boundary and the oxidizer at the oxidizer boundary were supplied exactly at stoichiometric condition. If phi is less than 1, that means that you have supplied less fuel than what is needed for the stoichiometric condition. But you see, the reason it's a bit confusing, because when the fuel and oxidizer are completely consumed, they are supplied at stoichiometry, but this at the reaction sheet, not in the initial condition, not in the boundary condition, okay? So that's why the word initial here is important. So now we obtain the location of the sheet. Now the same expression can be used to obtain the profile or the structure or the value of the mass fraction of the fuel or the oxidizer, because in the region where there is no oxidizer, this is 0, and so YF is equal to the right-hand side. In the region where there is no fuel, this is 0, and so the right-hand side is equal to negative the mass fraction of the oxidizer. And so this is actually written here. So now you have a complete solution that you have determined the YF, the YO, including the position of the reaction sheet. Okay. Next, you can use the other two coupling function, which involve the temperature. Okay. Remember that we can construct two other coupling functions. Okay. They are also conserved scalar when the Lewis number is 1. And if we solve for these two combinations, we get, again, two simple relations with the same exponential, e to the mx, right? Now, where YO is 0, that gives you the temperature. And where YF is 0, the second one gives you the temperature. So here is the temperature. So the temperature is given by those two expressions on the fuel side and on the oxidizer side. And of course, the common temperature at the position of the reaction sheet is the flame temperature. And this is the adiabatic temperature, which is not the adiabatic flame temperature, but is the adiabatic temperature for diffusion flame, which is defined as the temperature where the fuel and oxidizer are both totally consumed. Okay? Okay, so here is in fact a graph that shows you the profiles of the fuel in blue, the oxidizer in green, and the temperature in red. And I wrote here the adiabatic temperature and the position of the flame sheet in terms of in dimensional quantities, okay, in terms of dimensional quantities. There are a couple of comments that I want to make, and then we're going to take a break. The first one is that note that the solution has a discontinuity in slope at the reaction sheet. Now, this is not physical. Physical solution have to be continuous, have to be smooth, continuous and smooth. Now, this is a continuous solution, but has a discontinuity. So really, one have to ask, is the solution valid in this region? And if it is, we have to show that there is a solution of the governing equation that can smoothly connect the two parts of this curve. Okay? If we don't do that, then we are not guaranteed that we have a true solution of the governing equation. Similarly, there is a discontinuity in YF and discontinuity in YO at the reaction sheet, and the same question goes there. Now, Burke and Schumann, of course, did not address this, but later on, this was done using asymptotic methods, in other words, zooming on this region and making sure that indeed a solution exists. And in fact, out of this came more interesting results, which I will describe in the next hour. But that is one of the points that I wanted to raise. The second point I want to raise, which is just a minor thing, but one which is related to a parameter that will come later in the discussion, and at this point I want to bring it up. Note that I have put here the slopes of the temperature in a dashed line on the fuel side and on the oxidizer side. And you see that the two slopes are not, it's not symmetric. But what is the slope? The slope dt dx is like the heat flux, right? So it's the heat flux or the heat conducted to this side of the flame, and this slope is proportional to the heat conducted to this side of the flame. Now, what the solution showed that in general, there is the heat conducted to one side doesn't have to be equal to the heat conducted to the other side. In other words, it could be there could be a heat may be conducted on one side more than on the other side. Okay, we're going to see how this what the solution tells us. Since we know the solution, we can calculate the slopes. But another point is that the total heat conducted away to both sides must be, of course, equal or related or proportional to the total heat release, clearly, right? Because there is no other heat that is generated except that at the sheet. And so here I have a calculation. I don't think it's in your notes, but essentially it showed that the total heat conducted to both sides is indeed proportional to the heat release. And the other one, which is the more important one that I want to show you, is this parameter gamma that tell you gamma represents the excess of heat conducted to one side from the total heat generated in the reaction zone. In other words, the denominator is the total heat generated, and the numerator is the difference in slopes that tells you how much more is conducted on one side or another. And I called it gamma, and when you calculate it, it turned out to be exactly phi minus 1 divided by phi plus 1. I think that this is true only if, well, we are doing only unity Lewis number, so it's only true for unity Lewis number. Because you see, when Lewis number differ from 1, then diffusion can, in fact, vary those things a little bit. So anyway, so it's this, that. So what it tells you is this. If phi is less than 1, which correspond to a lean system, meaning that the supply of fuel is relative to that of oxide is less than what is the stoichiometric proportion, right? And so if phi is less than 1, which I interpret as a lean system, then clearly gamma is negative. Gamma negative indicate that more heat is conducted to the fuel side, which is not surprising because you see in the Burke-Schumann limit, you force all the fuel and all the oxidizer, right? It's infinitely fast chemistry. So all the fuel need to be consumed. So if it all has to be consumed and the fuel is supplied less than stoichiometry, then clearly there must be more heat conducted to that side in order to consume both at the sheet, right? And if phi is bigger than 1, in rich system, then gamma is positive, and so more heat is transported to the oxidizer side. And if phi is exactly equal to 1, then you will obtain that heat is conducted on both sides equally. Now that parameter turned out to be an important one when we analyzed the structure, and so I wanted to bring it up here before we move on. Let's take a break, and then we will do the problem for arbitrary Lewis numbers.